Welcome back to ME 760 Engineering Analysis 1. So we are continuing the same business of finding the series solution for ordinary differential equation of the second order. The last couple of lectures we found the solution for the ordinary regular points. Then last lecture we start to find the solution for the regular singular points. And again, last time we mentioned that we have three cases. The first case is we have two distinct roots for the indicial equation. R1 is different from R2, and R1 minus R2 they are not equal to, the difference is not equal to integer. Then today's lecture we will look for the case where we will have R1 equal to R2, and also R1 minus R2 is equal to integer. So let's continue. So we will look for equal roots. R1 equal roots, R1 equal to R2. So last time we checked the case for R1 does not equal to R2. So now we will look for, and also it was not, besides it is not equal to R1 equal to R2, the difference does not equal to an integer. So now we will look for the case for R1 equal to R2. So obviously we will be getting only one solution. And this one solution is just y of x. This is, we call it y1 will be equal to x R1, the summation from n equals 0 to infinity of an x to the power of n. So we need another solution, and this solution should be linearly independent from y2. So I will postpone finding the other solution here. Then I will jump into the third case, which is R1 is different from R2, but the difference between both of them is equal to a whole integer. So the third case that we will look here is just roots. Roots, they differ by integer. So let's say R1 is greater than R2, but R1 minus R2 equal to some integer m. So again we will have one solution again where y1 of x will be equal to x to the power of R1, the summation from n equals 0 to infinity for an x to the power of n. And y2 of x will be x to the power of R2, summation from 0 to n, pn, bn, x to the n. But in this case, we have to take into consideration that may or may not give a second linearly independent solution. Linearly independent solution. So this method may or may not give a linearly independent solution. So let's show how we will do it. By just getting to solve an example here. So let's assume our method is, our differential equation is x minus 1 multiplied by y double prime plus 3x y prime plus y equal to 0, and we will call this equation number 1. So how we will transform this to general form of the second order linear differential equation? We'll divide by this. So y double prime plus 3x, x will go out with x here, and this will give you 3 divided by x minus 1 multiplied by y prime plus 1 over x multiplied by x minus 1 multiplied by y equal to 0. So what are the singular points here? 0 and are they essential singularity or regular singularity? How we will know if they are essential or regular? So multiply here by, this is the first one, we'll multiply here by what? X. So, and then when you multiply here by x, if x equal to 0, substitute at x equal to 0, for example. This will give you what? 0. So it is at x equal to 0, it is what? 0. So it's analytic. And here, multiply by x equal to what? By x, so x will eliminate with x. Substitute when x equal to 0, this will give you what? Still a number. So it's not infinity. So x equal to 0 is what? Regular. X equal to 1. You multiply here x equal to what? X minus 1. Will cancel with x minus 1, and you will be left with what? With 3. And then here you will multiply by what? X squared. Yes? Yes, x squared, which is x minus 1. So this will give you what? 1. X minus 1 will go with x minus 1, and you will end up with x with 1 over x equal to 1. So this will give you 1. Okay. So we do not have any singular. So this is what? Regular singular points. So how we will solve? The steps that we discussed last time on how to solve this equation is we will just assume first that what? Y of x is x to the power of r, summation from n equals 0 to infinity, an x to the power of n. Then we will substitute in the differential equation, equation number what? Equation number 1. So we will get summation from n equals 0 to infinity of n plus r multiplied by n plus r minus 1, all multiplied by an x to the power of n plus r minus 2 plus 3 over x minus 1, summation for n plus r multiplied by an multiplied by x n plus r minus 1 plus 1 over x multiplied by x minus 1 multiplied by the summation again of an x to the power of n plus r, and this is equal to 0. Again, this is x to the power of n plus r minus 1. I can multiply here by x and divide by x. Yes? So if I multiplied here by x, then divide by x, I can take this x, raise it here, and this will be what? Minus 2. And in this one, I can multiply here by what? By x, and this will be x squared. Yes? And the x squared will be raised with what? Up here, so it will be minus 2. So the final formula will be just x divided by x minus 1 and this is r minus 2. And this will be n, excuse me, n plus r minus 2. So what's the next step? Next step is to find the indicial what? Indicial equation. But before we do the indicial equation, we have to divide by what? Divide by x to the power of r minus 2, both sides. If you do this, you will end up with this equation, summation. I will just remove this one from here so that I can write clearly. Summation from n equal to 0 to infinity. And this will have n plus r multiplied by n plus r minus 1 plus 3x over x minus 1 plus x divided by x minus 1 all multiplied by an x to the power of n equal to 0.
On that second term, are you missing n plus r?
Thank you. So because we have in the denominator here, for those two terms, we have x minus 1. I can multiply both sides by x. Multiply both sides by x minus 1 so that I can get rid of x minus 1 from here, and this will give me again summation from n equals 0 to infinity, and this will be x minus 1 multiplied by n plus r multiplied by n plus r minus 1 plus 3x multiplied by n plus r multiplied by plus 3x all multiplied by an x to the power of n equal to 0. What's the next step? Is to set x equal to what? 0. Set x equal to 0. So when you set x equal to 0, this is 0, so you will have negative 1 here, and this term will eliminate, this term will eliminate. So we will have what? We'll have negative negative multiplied by n plus r multiplied by n plus r minus 1 all multiplied by an. So all an will vanish except a naught. So in this case, this will be a 0 and n is 0, so this will be r minus 1, and this is 0, so this should be what? Minus r, and this is equal to 0. So a naught does not equal to 0, so the initial equation will be just r multiplied by r minus 1 equal to 0. So this is the initial equation. So what are the solutions for this equation? R equal to 1 and r equal to what? 0. So we have r1 equal 1 and r2 equal to 0. And what's the difference between r1 and r2? r1 is greater than r2, and the difference is equal to what? 1, and this one is what? Integer, and this is the case that we are studying. So we knew that R1 equal to 1 will give a solution, but R2 equal to 0 may or may not give a solution. So it may or may not give a solution. So from the last equation, we will call this equation number 2 here. So we require the coefficient of x to the power of n in 2 to vanish. And the coefficients are n minus 1 plus r multiplied by n minus 2 plus r multiplied by a n minus 1 minus n plus r minus 1 a n plus 3 n minus 1 plus r a n minus 1 plus a n minus 1 equal to 0. Somebody will ask, what did you get? N minus 1 and n minus 2 and so on. I have to warn you that this is x minus 1 here, yes, and you multiply, so you have x minus 1 here, yes, so you have to separate every term. So when you have x here, and this is x to the power of what? N, so this will give you x to the power of n plus 1, but we need the x to the power of n, yes, so you will substitute n equal to n minus 1 to get the power of x to the power of n, yes, so you will get an a n minus 1 term, and this is what you get here. Okay guys, and then you will have also, if you have x, if you have all of them, you will have the x's here. So you have x here, and you have x here, and you have x here. Okay guys, the only way that you did not have a n minus 1 is this case, is the 1 here, yes, because the 1 is multiplied by what? N plus r plus n plus r minus 1 multiplied by a n x to the power of n. So what's the coefficient for x to the power of n? A n multiplied by n plus r multiplied by n plus r minus 1. Did you understand what we did? Did you understand this? I want everybody to understand how you collect terms. Okay guys, because you do not have equal exponents. You do not have all of them has x to the power of n. When we have all of them has x to the power of n, it's easy just to pick up the coefficients for x to the power of n. But in this case, this x, if you multiply it by x to the power of n, will give you x to the power of n plus 1. So you cannot take the coefficient for x to the power of n plus 1. You have to take the coefficient for x to the power of n. So I can substitute with n equal to n minus 1. So if you substitute with this, n plus 1, when you substitute with n equal to n minus 1, this will give you what? A n minus 1, and the coefficient will be n minus 1 plus r, n minus 1 plus r, n minus 1 minus 1 is n minus 2 plus r, n minus 2 plus r, the first one. Okay guys, did you understand? Okay, so let's move on to simplify this equation. So when you simplify this equation, you will notice that this is equal to, what is the last one? You will notice that this is equal to n minus 1 plus r multiplied by n minus 2 plus r plus 3, all of this, and then plus 1 an minus 1, and then we'll simplify this to n plus r minus 1 multiplied by n plus r plus 1 plus 1 an minus 1. Again, this will give you n plus r all squared minus 1 plus 1 an minus 1, and finally this will give you n plus r all squared multiplied by an minus 1. And actually there is a step between this and this, that n plus r multiplied by n plus r minus 1 multiplied by an is equal to the remaining, those three terms. So it's equal to n minus 1 plus r multiplied by n minus 2 plus r multiplied by an minus 1 plus this term 3n minus 1 plus r an minus 1 plus an minus 1. So you collect all the an minus 1 in one side, and here you will have, let's say this is 1 and this is the term number 1. So this is equal to n plus r multiplied by n plus r minus 1 multiplied by an. So you have here n plus r, and here you have n plus r square. So it will cancel, and you will have an equal to an minus 1 divided by n plus r minus 1 multiplied by n plus r. So let me and this is the recurrence relation that we are looking for. So let's call it star. Then what's the next step? Next step is to substitute with the values for R1 and R2 and figure out what's the coefficients. So for R equal to R1 equal to 1, if you substitute n plus r is 1, so this is n plus 1 over n plus r minus 1, n is 1 and minus 1 is 0, so this will give you an equal to n plus 1 divided by what? Divided by n multiplied by an minus 1. And this is the relation that we are looking for. If we set A0, we said that A0 does not equal to 0. We set A0 equal to 1, for example. So we will get A1 equal to 2, A2 equal to 3, A3 equal to 4, and AN equal to n plus 1. Now, the solution y1 of x will be just x to the power of r1, and r1 is 1, so this will be x to the power of 1, summation from n equals 0 to infinity, multiplied by an multiplied by x to the power of n, and an is just n plus 1, so we'll remove this one and put n plus 1. And this holds for the absolute value of x less than 1. Why?
That's equal to 1, it seems.
So we solve it here for around x equal to what? If we said that the y of x equal to summation of an x to the power of n. So this is the expansion around x equal to what?
0.
Yes, because if we expand it around x equal to 1, it will be x minus 1. Yes? So we expand it around x equal to 0. So this is valid until you hit the next singular point, and the next singular point is at x equal to 1. So the radius of convergence for this solution is absolute value of x less than or equal to what? 1. And this is why I put here x is less than 1. So this will give you x multiplied by 1 plus 2x plus 3x cubed plus, and if you just solve this, you will notice that this is x divided by 1 minus x whole square. So this is the polynomial expansion. If you get 1 minus x to the power of minus 2, and you expand 1 minus x to the power of minus 2, you will get this expansion here. So this is the solution. So you can leave it at the series solution like this, or you can solve it and leave it to analytical form like this. So if you solve this equation analytically using another method, for example, instead of the method for the series solution, you will reach to the same conclusion here. So let's look for the other solution where r equals to what? R2 equal to 0. So for R2 equal to 0, R2 equal to 0, we will return back and substitute in our equation star 0, so n plus 0 is n, and n plus 0 minus 1, so n minus 1. So an equal to n divided by n minus 1 multiplied by an minus 1. So now we require that our a0 does not equal to 0. Yes, guys? So now, what's a1 from here? a1 will be what?
0.
Will be 1 divided by 1 minus 1 multiplied by a0. And this is equal to 1 over 0 multiplied by a0. If a0 is equal to 0, there is no problem. Yes? 0 multiplied by anything will be 0. But we require that a0 does not equal to 0. So a1 will be what? Will blow up. So a1 is infinity, and this method will fail to find y2 of x, because we will not be able to find any solution for this case. Okay, guys? Okay? So we have a note here that if x equal to 0 is not a singular, but it is a regular point, a regular ordinary point, regular ordinary point, and R1 minus R2 equal to integer, we would have two independent, linearly independent solutions. So if x equal to 0, is a regular point, it's not a singular point, we guarantee that we will have two solutions. So when we started the series solution, we knew that what? We knew that we will have, if the function is analytic and it does not have any singularity, we guarantee that we will have what? Two independent solutions. Yes? But in this case, if x equal to 0 is regular and it's not singular one, and we have r1 minus r2 equal to m integer, we will have two independent solutions. Somebody will ask, but in the case for the regular point, we do not have r. Because r1 is 0 and r2 is 0, because we do not solve the Frobenius, we solve y equal to summation of an x to the power of n, so there is no r. Yes, so r1 is 0 and r2 is 0, so r1 minus r2 is integer is 0, 0 is integer, is among the integers, and we have a solution. Yes, okay guys, so we do not have this problem where r1 minus r2 is equal to integer, may or may not find the solution. This is only when you solve around a regular singular point. Okay guys, so for a regular point, there is no problem. As long as you do not have any singularity, everything works okay, you will find a solution, two independent, linear independent solution. If you have singular points, now if R1 is different from R2 and the difference is not integer, you will get two independent solutions. R1 equal to R2 or R1 does not equal to R2 but the difference is integer, you may or may not find a second solution from the R2. So how you will get another solution now? In the handout that I give it to you guys, there is a couple of methods. One is using the Wronskian, and the other one is using the general derivative method. So if you go back, and I will be writing here the first of those two solutions, which is the Wronskian. This is in section 7.5.1 in the handout that I uploaded in line page 286. If you want to read more about this. So this is finding a second solution if R1 equal to R2 or R1 minus R2 equal to M, where M is integer. So the first method is the Wronskian, and this is section 7.5.1 in the handout in page 286. And so if we have a differential equation, y double prime plus p of x multiplied by y prime plus q of x multiplied by y equal to 0, and we have two linearly independent solution, y1 of x and y2 of x are linearly independent solutions. We knew that the Wronskian is just equal to the determinant of y1 and the derivative of y1, y2 and the derivative of y2, and this is just y1 y2 prime minus y2 y1 prime, and we will call this equation number 1. Then if we divide equation 1 by y1 squared, the square of the first solution. So this gives us the Wronskian divided by y1 squared equal to y1 multiplied by y2 prime divided by y1 squared minus y1 prime multiplied by y2 divided by y1 squared, and this is nothing more than the differentiation of y1 over y2. Yes? Do you have any comments here? So what we will do right now is just say that y1 of x is nothing more than y2 of x multiplied by the integration of omega over y1 squared dx. And we will call this 2. Maybe instead of just somebody will be confused if this is x, so we can call this du, and this will be a function of u, and this is a function of u, and the limits for the integration will be over x. So that I can of course change the symbols of integration without changing anything. So now we want to find, if we want to get, actually this is, you did not catch the mistake that I did, guys. Nobody told me that I did a mistake. So now, in order to find the second solution, I have to do what? To multiply the first solution that I have, multiplied by what? Wronskian divided by y1. Okay, y1 I have, y1 squared I have. But the Wronskian is the multiplication of, it's a determinant, and it contains y1 and y2. So I return back to the same problem. So I have to find out how to figure out what's the Wronskian. Okay, so that I will get a feeling of what we are doing. So we need to find the Wronskian. So to find the Wronskian, we will just differentiate equation number 1, which is just this equation. Okay, guys? We'll differentiate this equation. So omega prime equal to minus equal to y1 y2 double prime plus y1 prime y2 prime minus y2 y1 double prime minus y2 prime y1 prime, and this is just equal to y1 y2 double prime minus y1 double prime y2. But what do you think, guys? y1 and y2 are what? What? y1 and y2 are what? Linearly independent solution. For what? For the differential equation. So if I substitute with y1 and y2 in the differential equation, they should satisfy the differential equation. Yes? So in this case, both y1 and y2 satisfy the differential equation, which is yi double prime plus p yi prime plus q yi equal to 0. So in this case, I can substitute in the Wronskian equation by putting, let's say, y1 here, and then y2, and substituting y1, for example, in terms of y2, and so on. So this will give me y1 multiplied by y2 double prime. You will get y2 double prime from here. y2 double prime is just p multiplied by y2 prime minus y1 prime, y2 plus y2 multiplied by p multiplied by y1 prime plus q y1. You will notice that this term will cancel out with this term if you multiply y2 here and y2 1 here.
Should that first term that you crossed out there have a q in it?
Which one?
That first term you crossed out?
Yes, so what I did, so it should be q y2. Yes?
Yeah.
Q y2. Okay? And if you do this, you will end up with b minus p multiplied by y1, y2 prime minus y1 prime, y2, and this will give you minus b of x. What's this? From equation 1. So this is what? Wronskian. Yes? So we end up with equation Wronskian, the derivative of the Wronskian equal to b of x multiplied by the Wronskian. Yes? So you can solve this equation and you will get that the Wronskian is just equal to what? Some constant c multiplied by exponential function to the power of b of x, or b of u, let's say b of u du, and here's x. Yes? This is just differential equation. Omega prime over omega equal to b of x. This is the solution of this equation. D omega by dx over omega equal to b of x. So d omega over omega equal to b of x dx. And this is ln, and this is b of x dx. Then you will solve, you will get c multiplied by e to the power of p of u du integrated over du, and the limits of integration will be just x. Yes?
Should there be a negative sign in front, or
There is a negative sign. A negative sign here.
and on the top, Yeah, because I was wondering how do you cancel q y1 y2 when they're both positive. So something should be negative there.
The
The first
q,
one should be-
y2 should
Yeah,
be
this
positive.
one.
Yeah, it should be positive.
It should be positive inside your brackets.
Yeah, it should be. Yeah. Sorry for the mistakes, guys.
It's okay.
Okay, guys. So we can substitute with this equation in what equation? In equation number 2. And we will use c as equal to 1. And then we will get the final formula for y2. A final formula for y2, and y2 will be of x will be just y1 of x multiplied by the integration over x of 1 over y1 squared of u multiplied by the Wronskian. The Wronskian now is e to the power of minus the integration of p of v dv, and this integrated over du. So again, this is the method, and this is how to use y1 to get what? to be y2. The problem is how to find this big bulky one here, how to find the integration. So if p of x is constant, very easy, e to the power of constant, integration of a constant, this will give you exponential function. You have y1 squared, solve the integral. But also if y1 is not analytic and it is a power series, it will give you a very hard time to integrate even exponential function divided by a power series. And the power series is a square. So we will look for the more easier way next time, which is we call the derivative method. And I think the last problem in your homework number 7 depends on the derivative method that we discussed here in the class. So hopefully, if you need any example, you just look at the hands out for this section, and you will notice that there is an example there in the book that uses the method. So just consult this example and tell me if you have any question next time or not.